Okay. So now we're going to the fourth presenter. So that's Marcel Moosbrugger. Are you there, Marcel? Yes, there.
Yes, I'm here. I'm going to share my screen.
Excellent, excellent. So while you share your screen, I introduce this paper. So this is another short tool presentation on the probabilistic termination tool called AMBER. And as for the previous speaker, you have about 7 minutes of presentation, and then maybe you will get some question. Otherwise, I will ask one. Please
Sounds
go ahead.
good. Sounds good. So as mentioned, I'm going to present to you today the probabilistic termination tool AMBER. This is joint work with Ezio Bartocci, Josvita Katun, and Laura Kovac. So let's jump right into it with a concrete example. And let's take this probabilistic loop here on the right side. So it initializes two variables, x and y, both by 0. And then in every iteration, it either increases or decreases both x and y with probability 1/2 each. So this is basically a random walk inside this white circle, and the loop terminates. It's like here in the loop guard whenever this red dot walks out of the white circle. And now you can take a guess. Is this loop terminating? Does it always terminate? And if we would zoom out and trace the path that this red dot is taking, this is what a typical simulation would look like. So although this is a very small program, it can already give rise to quite complex behavior. But still, being able to check, in the ideal case, automatically check for probabilistic termination is also important for the safety of stochastic systems. But as we all know, this is a hard problem, because even in the deterministic version of this problem, we are faced with the halting problem, which is undecidable in general. And even more, for the probabilistic version, we have these two concepts, which is finite expected termination time, which is called past, which is actually different from termination with probability 1, which is almost sure termination, or AST. And now with our tool, the idea is you can use our tool AMBER, which is a probabilistic termination analyzer written in Python, to automatically check for past or AST or refute these concepts for some specific probabilistic programs. So maybe you have guessed the previous example to be positively almost surely terminating, so having a finite expected runtime. But what about this one? It gets a bit more complicated. So we draw from some distributions, like in this case, the Gaussian distribution. We have polynomial arithmetic here in the loop guard as well as in the loop body. Also here, the C is a symbolic constant. It's not a program variable. So it's a symbolic constant, which basically represents any arbitrary real number. So now you can again take a guess or get out a pen and a paper and try to figure out if this is positively almost surely terminating or almost surely terminating. Or now you can just take our tool and let's feed this program to our tool AMBER, and it will do a few computations, which I'll explain a bit in a bit, and then it will tell us, yes, this is actually positively almost surely terminating, and therefore also almost surely terminating, and it will also give us a witness to certify this result. So we have the answer. But as I said, there are also programs which terminate with probability 1, but have an infinite expected runtime. A very famous example here is, and also a very minimal example, is the one-dimensional random walk, the symmetric one. So you either increase or decrease with the same probability and also by the same step size. Or, of course, you can have programs which have a non-zero probability of not terminating, of diverging. And also, like the AMBER doesn't only check for termination, but also for these variants of termination or non-termination. And let's give AMBER, for example, the symmetric one-dimensional random walk. And this time a bit quicker, it will tell us that it is not passed, so it has an infinite expected runtime, but it terminates almost surely, and also gives us two witnesses for these facts. So what can we feed to AMBER? In essence, prop-solvable loops, which were introduced 2 years ago. And these are essentially loops like we've seen in the example. You have an initialization part, a while loop, we have polynomial arithmetic within, like basically arithmetic assignments involving polynomials, with a constraint that we have acyclic variable dependency. So for example, y here depends on x, but x does not depend on y, and also linear self-dependency. So all variables here, x, for example, have only a linear dependence on itself. The guard is any polynomial inequality over program variables. And as you've already seen, we support symbolic constants, which represent any arbitrary real values. So there is also some form of non-determinism here, and also common distributions like uniform and Gaussian and so on. So what is going on inside Amber, just to give you a quick gist. So we feed it such a loop. And then, as we've already seen in the first talk of the other day, there are plenty of different proof rules, which is how I call it, for proving either past or asked or refuting these concepts. And they have been introduced in the past few years. And Amber makes use of these, actually of 3 to 4 rules, which have been introduced, together with relaxations and specific algorithms that we developed of these proof rules for prop solvable loops. This was in a paper published this year. And in this tool paper, we also generalized these algorithms to include probability distributions and symbolic constants. And then Amber will, using these rules, give you a potential answer, telling you it's either asked, passed, or non-asked, non-passed, and give you some witnesses for it. So to summarize, Amber is a tool to prove almost sure termination or positive almost sure termination, or also to refute these concepts. It supports a class of polynomial probabilistic programs. It is fully automated, so you don't need to provide it any templates or invariants upfront. It supports symbolic constants and common distributions, and the code is publicly available on GitHub if you want to check it out. We also provide a Docker container for ease of use. And if you are interested in the underlying algorithms that we used, I recommend to check out our paper that was published at ESOP this year, or just visit our group's website for more information and for benchmarks. Thank you very much.
Okay, thank you, Marcel, for this nice presentation of the tool, and perfectly on time. And as has been common in this session, I don't see any questions. So I can, maybe there is one question. Otherwise I have one. Okay, so Christina has a question. Thanks for the interesting talk. Do the programs contain both probabilistic and mnemonic choices? Christina, if you're here, you can also just ask. But anyway, Marcel.
No, this is the question. I was wondering, thank you for the talk. I was wondering whether you can cover also choices with indifferent probabilities.
No, actually not. So, and also not, you said something about non-determinism. So they have to be constant. So the probabilities, the choices have to be constant. You can have symbolic constants, like there was one example here, which is a non-symmetric random walk, quite simple example. But they have to be constant. There are some theoretical restrictions why this is the case, and that would go too deep to explain it now, but there are some hints on this on this paper at ESOP, which I already mentioned.
Okay, Marcel, there's another question in the chat. Oh, sorry, Christina. Yes, so
no problem.
Marcel, there's another question in the chat. Do you see it, or you want me to read it?
Let me see if I can open it. Yeah, I can open it.
I can tell a few. So the question is, could these probabilistic programs be encoded into some probabilistic model checking tool as models, and then the past property analysis be analyzed with it?
Very good question. Actually not, because the tools that we heard so far, like Storm or Prism, they are on Markov decision processes or Markov chains, and they only work on finite states, basically. And already this very simple example here, which I showed, our infinite state, for example, this year is an infinite state system, and so you couldn't do it directly with it.
Yeah. Okay. Okay, thanks. And so a final question for me then. So next steps. What are you going to do next?
Next steps would also be to extend the program model. So as I said, we don't need invariants and all templates, but basically our program is kind of a template. So that to extend that to support if statements and all nested loops. And I found the first talk very interesting. So I guess that's very much into my direction. And I should probably talk to the order if this lexicographic ranking supermartingales could be somehow included as well in our mechanism.
Okay, so that sounds like you have enough to do.
Yes.
Okay, so good luck then with continuing this, and thanks for this nice presentation once again.